the Milky Way. And we're not actually at the center of our galaxy. We're a little bit off from the center of the galaxy. And then there's the neighboring galaxies and so on and so forth. But then we have talked about how when we are interested in something as specific as a planet, a solar system, or even a galaxy, or even say our galactic center, which by the way has a lot of radio sources, X-ray sources, things like that, because there's a supermassive black hole that we've also talked about in our lives at the center of our galaxy, and it actually accretes more mass from its neighboring objects, and that accreting mass can give off radiation because it's accreting. It's getting the black hole is eating something, and all that stuff that's getting eaten is falling into the black hole and going through acceleration, and at those levels you can get something like synchrotron radiation, for example. And we see that radiation as radio sources, X-ray sources, things like that. So sometimes around a black hole can be quite bright, even though a black hole itself is dark and it traps light, even light. But something like this, a supermassive black hole, our solar system, our sun, other stars, us, these are all still pretty specific types of things and fall sort of more under astronomy and astrophysics. So, you will get to see a 3-hour water break. So, what I have in mind for you tonight is actually when we zoom out of all of this and think about the universe as a whole. So that falls under the topic of cosmology, which is to understand the universe more broadly. So way back when, there were no galaxies, there were no stars even, and the universe was just getting started. It was forming. Something like the Big Bang happened, and even in that sort of environment, what types of things may or may not have been there already, what things were forming, and eventually, as we know the universe now, as it has gone through a lot of evolution, the universe itself has gone through evolution. So we have talked a lot about even our planets forming, right? That has gone through evolution. Even stars have life cycle. That stars go through evolution, but the universe as a whole has actually gone through evolution. And the makeup of the universe, what makes up the universe, the composition of the universe itself has changed. So you might wonder, what are the main ingredients of the universe and how to understand the universe in a cosmological standpoint? Because you could be interested in specific astrophysical sources, and that's interesting too. All of it is interesting, right? Our galaxy itself has a lot of interesting things going on. So it really is up to you. If you want to study the universe or any smaller part of it, chances are that you're gonna study something very interesting. There's a lot of interesting things going on with all of this. But some people specifically want to understand some more sort of open questions, deeper questions, and something more large scale. So another way to think about it is the study of the universe entails, if you want to get into specific examples, the study of the universe entails understanding the Big Bang, sort of what the Big Bang did, the early universe, so within the first, say, 300,000 years of the universe, what was it like? Overall, what are the cosmic ingredients? What are the main ingredients, or what we call cosmic inventory? The hot and dense universe, yes. So exactly. So those things that you guys are saying, understanding broadly speaking, because we know at a fundamental level what sorts of things, for example, we're made of, but that's a lot of detail. But what are the 5 most fundamental cosmic ingredients? That's something that we have touched upon. We've actually covered in a lot of detail in the past, and I will cover again today. And then also the fact that the universe is going through evolution. And another topic to think about is large scale structure formation. So, like I said, when you care about specific sources or objects. What's an example of an object? The earth is an object, the sun is an object. Sometimes in astronomy, we say object because that's more general. Instead of constantly, instead of having to classify something, we might just say, oh, I found an object. That's my object. That star, it could be a star eventually. Maybe you don't know yet, that object. So when you're interested in something like an object or an event in the sky, so a supernova, if Betelgeuse were to supernova, a star, a very big fat star near, sort of near us, if that were to supernova, we would see it. That would be an event in the sky. It's a transient event. It could stay bright for some months, actually, but still, it's considered a transient event if it fades and later on it's not there anymore or not as bright anymore. So that's an event. So if you study such an event, if you study an object like a star, a planet, asteroid, a black hole, whatever, those are more under, again, astronomy or astrophysics. Betelgeuse, yes, I believe it's something like Betelgeuse, actually. So, yes, please, yes, come on in. Thank you so much. Juice, Betelgeuse, I believe, is the spelling of that. So those events, those objects, when studied, fall under astronomy or astrophysics. Astrophysics is more the study when you care about certain physical processes. If you care about how a star forms and what nuclear physics happens in order to make the elements, for example, that would be, specifically nuclear physics, which is sort of a branch of astrophysics in the realm of these stars, right? Of course, nuclear physics in the realm of some other thing, such as making the atomic bomb, is a little bit different, but some overlap is there as well, So basically, these I wanted to tell you a little bit about what the different subfields are, and then make the kind of distinction that these are much, much more specific than what we're about to talk about today, which is the universe. Only the universe. Okay, let me read a little bit from this first page of this book, which will further help you with an orientation to this topic. So, Einstein's discovery of general relativity in the last century enabled us, for the first time in history, to come up with a compelling testable theory of the universe. The realization that the universe is expanding and was once much hotter and denser allows us to modernize the deep, age-old questions. Why are we here and how did we get here? So these can be sort of existential, sometimes even philosophical questions, but we can actually study these in the standpoint or from a standpoint of cosmology, which is really pretty cool. So the updated versions of such questions could be, how did the elements form? Why is the universe so smooth? You will, you will see what I mean by the universe being smooth in a little bit. We have actually talked about it in the past, so if you've attended those lives, you have some idea already. But basically, even something like how did the elements form? We know that all the elements above helium were made in stars. This is going to be a lot more both broad and specific in the sense that, well, what about before stars? The universe formed before stars formed. And that's why we have to talk about the Big Bang. We have to talk about what things the Big Bang is responsible for. What things did it make? I'll tell you in short, or I'll tell you really quickly, that the Big Bang, pretty much the only element that it mostly made in terms of elements is actually just hydrogen. So the most abundant element in the universe is still hydrogen. And hydrogen was made in the Big Bang. A little bit of helium was also made, and trace amounts of lithium was also made. But mostly, all the elements above helium are, of course, made in stars. So even something like that, I guess, overall, from a big picture, could be thought of in terms of cosmology. how did galaxies form from this smooth universe or from this smooth origin? So, long story short, we also know like that we have galaxies in this universe, and there is a certain distribution of these galaxies in the universe. And in fact, that distribution is not random. So there is something to be understood about this type of large scale structure formation. So you might hear people talk about that, and that too is a topic under cosmology. Yes, very nice. So those types of things, that's basically in the realm of cosmology that we will be talking about. Remarkably, these questions and many like them have quantitative answers that can be found only by combining our knowledge of fundamental physics with our understanding of the conditions in the early universe. Even more remarkable, these answers can be tested against astronomical observations. So there's a lot of overlap between cosmology and astronomy, of course. Good thing that we've been doing astronomy for forever. I think astronomy is maybe one of the oldest sciences. This culture of observing and learning about the universe in an astronomical point of view has been around forever. Cosmology is a little bit more modern because, even around 100 years ago, we didn't actually know about the expansion of the universe and the existence of other galaxies, right? So this field, upon the discovery that there are more galaxies, and upon the discovery of the fact that the universe is expanding, really, really, really kind of opens up this more modern field, which is cosmology. Pretty much exactly what the universe is doing, and the fact, that is, if you didn't know that the universe was expanding, and in fact its expansion is accelerating, then cosmology might not be a field. That bit that I just said is a very important question in cosmology because it's related to what we call dark energy, because we don't know exactly why the universe is, we call it dark energy, but we don't know exactly what dark energy is. It's an open question. So this fact in itself, that the universe is expanding and its expansion is now known to be accelerating, this itself is probably like half, if not more than half, of what cosmology entails. You'll see. So now you already know. I spoiled it for you, which is that the field of cosmology, a lot of it has to do with dark energy. Number one open question of this universe is, what is dark energy? We don't know. We just know it's there. And then number two most open question of the universe is, what is dark matter? Now, dark matter, of course, has relevance in other contexts as well. For example, even in our own galaxy, we see that dark matter affects us and affects how things behave in our own galaxy. But you will see how dark matter has significance even from a cosmology standpoint. And so we must understand what cosmology tells us about dark matter. And it's almost like the dark matter stuff that we get from cosmology will join hands with the dark matter stuff that we get from astronomy, and hopefully give us a fuller picture about dark matter, which in itself, of course, is an open question and an open topic, and we don't know what it is. So there you go. Again, very long story short, open questions of the universe. Number one, what is dark energy? We don't know. What is dark matter? We don't know. And then third, I would say the most important open question of this universe is the origin of elements, which is not always quoted, but pretty much because there are a lot of elements that we understand pretty well, very well actually, how they're made. And then there are a few elements in the middle, somewhere in the periodic table, that we don't understand as well. So, of course, because elements are so fundamental, we are made of elements, right? Ordinary matter, obviously very fundamental. Understanding how some of these elements are made, if you don't know them, that's also a room for a lot of research in that particular topic. So, and it's interesting because all of this can be studied as part of cosmology. So that's what we will talk about. And it'll be a little bit different because again, these things can also be talked about in terms of astronomy and astrophysics, but they are also they also get approached in cosmology. But I will say the one question that is without doubt pretty much a cosmology it's a cosmology dominated question, that is probably the number one there, you guessed it, is dark energy. So because dark matter is an open question, we know it exists. There is evidence of dark matter. We have actually covered that in some lives before. There is evidence of dark matter both in our own galaxy and also from a cosmological standpoint. We will cover some of that today, actually, the cosmological evidence of dark matter. So we know that there is something extra, invisible matter, dark matter, however you want to call it. It's affected by gravitation, but it does not interact with electromagnetism or light. So we know that there is something. Invisible matter could be a word for it. Dark matter could be a word for it. But we know that there is evidence of it. We just don't know what it is. You're correct. We don't know what it is. And what I was just now saying is dark matter is one of those topics that is sort of, you can approach it from an astronomy point of view, astrophysics point of view, and also cosmology point of view. And it comes in all of these different subfields. Dark energy, on the other hand, if you're studying dark energy, then it's probably going to be a cosmology point of view, because dark energy, remember, has to do with expansion of the universe. So you need to zoom out and study it at that level. You can't just talk about dark energy in our galaxy. I mean, you can, but it's not a local kind of effect. It's a more cosmic effect, right? So for the cosmic effects, what's happening when you look at the universe as a whole, you have to zoom out and you have to talk about large scale. That is dark energy. Okay. All right. So we will talk about the idea of expanding universe. So by the way, I also had a live where I talked about Einstein's equations and a little bit of general relativity. We might not get into too much detail of those equations here today because I want to give the overview at a digestible level. But if you're interested in understanding some of the general relativity and basic equations, not questions, although we talk about questions too, but basically, if you want to be sort of prepared with the basic equations and tools that you need in order to sort of understand where the math is coming from in cosmology, then I have a live, I believe it's called Einstein's equations, in my live tab. You might have to scroll a little bit to find it, but it is there. So that is that. The success of Big Bang. So the fact that we have accepted now that the universe started with the Big Bang, which, by the way, the name is a misnomer. It's not very big, and there was probably not a bang. But anyways, we call it the origin of our, the starting of our universe. We call it the Big Bang. The name has stuck, but this is saying the success of the Big Bang rests on three observational pillars, the Hubble diagram exhibiting expansion. So expansion kind of means that we started small, started expanding. So expansion actually also gives us a proof that Big Bang theory is correct. Light element abundances, which are in accord with Big Bang nucleosynthesis. So another topic I mentioned, which we'll cover here under cosmology, is Big Bang nucleosynthesis. So remember, if you say that there is certain amount of some stuff now in the universe, it better match with whatever would make sense as part of the Big Bang, and vice versa. So it's almost like cosmology. Obviously, it's big stuff, quite literally, like universe math. Like, let's say you come up with a model for the whole universe, right? Well, whatever you're observing and know because of observation, it better match up very well with that early conditions, and however much stuff, say hydrogen, for example, was made in the Big Bang, or in your Big Bang nucleosynthesis model and understanding, it has to kind of all be consistent. So it's almost like we have a puzzle, and some of the pieces of it are observational. We make observations. We have certain tools of observation. By the way, because the universe has hydrogen is its most abundant element, you will see how we talk about absorption by hydrogen atoms, and that will give us clues as well as how much of each thing is there. But all of this stuff, like the observation and everything, has to all be kind of consistent. And the one, say you don't know something, it has to make sense with the rest of the picture in order for you to accept it as the answer. And you will see how we end up with dark matter and dark energy as part of the cosmic ingredients because of things like that, okay? Because of this type of puzzle solving, basically, where some of it is observation and some of it is a model, right? So light element abundances which are in accord with Big Bang nucleosynthesis. So Big Bang nucleosynthesis is probably the theory and the models giving us how much of the, what kind of nuclei and other things were there. But then light element abundances are more of an observation, and they better match what the Big Bang people are saying, okay? Or the Big Bang people better match what the light element abundance observations are saying, if that makes sense. And it does. So that's another win for the Big Bang people, the Big Bang theorists, let's say, okay? Ooh, and then the other thing is the black body radiation left over from the first few 100,000 years of the universe, which is, of course, the cosmic microwave background. Another huge observation that keeps coming up that you will note and hear about in cosmology is, of course, the cosmic microwave background radiation, which is from the first few 100,000 years. It's actually like 300K years old. And these photons and these photons that are just chilling there still, and we can, it's like when we see them, we are basically observing a time that is older. It's like looking back in time. And that too can tell us something about the Big Bang. And all of these things that we learn have to all be consistent. So that's what this is saying. So after introducing all this, now let me talk about developments in the last 2 decades of the 20th century. So I already told you this, but I'm going to give it to you in the author's language, which is that, so what are we doing here, right? Developments in the last 2 decades. So this is relatively newer stuff. It's not as old. It's modern cosmology. It's a more modern science. So in the last 2 decades of the 20th century, so we're now in the 21st century, so maybe this is more like 40 years old at this point, or whatever the math is. Both theoretical and observational point to the existence of dark matter and perhaps even dark energy, the need to understand the evolution of perturbations around the zeroth order smooth universe, and inflation, the generator of these perturbations. So that's what, in cosmology terms, they're going to be looking into. But I think the way I said it was the more general way, which is that we don't know what dark energy is. We know that there is expansion of this universe. In fact, this expansion is accelerating. We want to understand what that is, what's doing that. We call it dark energy, but AKA, we don't know what it is. There is also evidence for invisible matter or dark matter. It's a thing that we need by these equations, not only in astronomy, but also in cosmology. So there's a cosmological standpoint for why we need this extra matter. So we don't know what dark matter is. So that's question number 2. And then number 3 is the elements, like I mentioned. So we have good evidence that the universe is expanding. This means that early in its history, the distance between us and distant galaxies was smaller than it is today. Have you heard of Hempel's paradox? I don't think so. It is convenient to describe this effect by introducing the scale factor A, whose present value is set to 1. At earlier times, A was smaller than it is today. We can picture space as a grid, which expands uniformly as time evolves. Points on the grid maintain their coordinates, so the co-moving distance between 2 points, which just measures the distance between coordinates, remains constant. However, the physical distance is proportional to the scale factor, and the physical distance does evolve with time. So it looks like these boxes that are going from smaller to larger as the universe evolves and expands. So this is the expansion of the universe. The co-moving distance between points on a hypothetical grid remains constant as the universe expands. The physical distance is proportional to the co-moving distance times the scale factor, so it gets larger as time evolves. We introduce the scale factor with this symbol small a because you will see how a lot of the math involves that. Some of the math I've covered in previous lives, namely that Einstein's equations live that I mentioned. So I might not get into too much of that here today, but it is important to understand those types of equations as well. And the concept of the scale factor is so basic that I thought I will say it again here. And the other thing is, so let me real quick tell you about this part as well. It's a little mathy, but it's not too mathy. To understand the history of the universe, we must determine the evolution of the scale factor A with cosmic time T. So this scale factor thing that I just mentioned, turns out that it evolves as well with time. It is not going as the same function of time as it does now, as it did in the beginning of the universe and as the universe evolved. So we'll get into a little bit of that here. General relativity provides the connection between the evolution of the scale factor and the energy in the universe. So it turns out that the makeup or the composition, what the universe is made of, has kind of changed. As you said, I think someone said here that the universe in the beginning was very hot and dense. So what is that? Hot and dense. Hot and dense. Crazy photons. Photons hitting everything, making everyone hot and energetic, making everyone excited. Too much photons. You can't calm down because of photons hitting you. That is called a radiation-dominated universe. So if you hear those terms in the context of cosmology, that's what that means. In the beginning, the universe was like how I was in the beginning of the live. Very excited. Photons were the king of the jungle. Photons were hot. Photons were excited. Photons were crashing into each other, and electrons. Photons, as in photons were also colliding with electrons. Photons would hit you and get you excited and not let you become a neutral atom. Now, hydrogen is just a proton. So by the way, we basically just had nuclei, Big Bang nucleosynthesis. We didn't have enough calmness in the beginning of the universe or shortly after the beginning of the universe to make really neutral atoms. We're really just talking nuclei at that point. Okay, so nucleosynthesis, nuclear stuff. Protons, add neutrons, becomes a different nucleus, a different element. We say element because a unique element is given by how many protons is in its nucleus. But actually, generally speaking, an element means that there's an atom, there's an atom, inside of it there's a nucleus, then there's one or more electrons going around the nucleus. That is the more traditionally when we talk about elements. But think about it in terms of a mess, of a hot, messy, energetic, crazy environment. You don't actually, at that point, generally speaking, you won't get neutral atoms and elements as we know and love here on Earth for the most part. You will get a nuclear kind of environment where nuclei are getting made. And even then, there might be trouble and there might be scarcity. We will actually see how in the beginning, in the radiation-dominated universe, there wasn't enough of the helium nuclei, for example, to make carbon. Because you might have asked me, right? You said that in Big Bang nucleosynthesis, we had hydrogen, of course, mainly hydrogen. Why not? Because hydrogen is simply a proton. The hydrogen nucleus is the most simple thing. It's a proton. We will get into its isotopes, but the simple hydrogen nucleus is just a proton. So yes, there were protons. Yes, there was hydrogen, and yes, there was a little bit of helium because hydrogen helps with that, but very small lithium, pretty much not worth mentioning amounts of lithium because it wasn't stable enough for these things to happen without getting hit. Also, there weren't enough of the helium nuclei which you would gather together and, do stuff with in order to make the carbon. To make carbon, you need stars. So the first generation of stars, as when they formed, they started to make the heavier elements, or what we call metals in astronomy. Everything above helium is pretty much a metal in astronomy. So coming back to this scale factor, as I'm saying that the universe has really come a long way, the universe is not today, the universe is not like how it used to be. How it used to be was different. We call that time radiation dominated. It became matter dominated. Now we will see where it's at now. It's got a lot of dark energy, spoiler, at this current time, dominated. But with this type of behavior, with its evolution, the scale factor also changes. So the dependence of the scale factor on cosmic time t varies as the universe evolves. At early times, A was proportional to t to the 1/2. So A, what am I doing? A was proportional to t to the 1/2 in the early universe. At later times, this dependence actually switches to t to the 2/3. So interesting. How the scale factor varies with time is determined by the energy density in the universe. At early times, one form of energy, radiation, all of the stuff I was just talking about, dominates. So at first, when the radiation was dominating in the universe, in the radiation dominated universe, the scale factor went as t to the 1/2. In a matter dominated universe, the scale factor goes as t to the 2/3. So at later times, non-relativistic matter accounts for most of the energy density. In fact, one way to explore the energy content of the universe is to measure changes in the scale factor. We will see that partly as a result of such exploration, we now believe that very recently, the scale factor has stopped growing as t to the 2/3, which is what we believe it was going as. In a matter-dominated universe, it has now started to change again recently, which is also a signal that a new form of energy has come to dominate the cosmological landscape. And this is where we will talk about dark energy in a little bit here. So again, radiation-dominated universe, the scale factor went as t to the 1/2. Matter-dominated universe, the scale factor went as t to the 2/3. And then it changes again more recently now, giving us an indication that the energy content of the universe is evolving and has changed again. So, and then there are some equations coming from general relativity and our discussion here of the universe, what it does, and getting into it, some of the observational things as well. We've covered this in the live before called Einstein's equations. So we will skip some of that for now, but I did want to mention to you about the scale factor and cosmic time, because those are important concepts and we'll kind of keep coming back up, okay? So now we will go to another part. That was just a little bit of an introduction to what we are going to be talking about. Now we'll get into more of the meat of it. I wanted to mention about Big Bang nucleosynthesis. This is something we also mentioned in the past, but I think it's worth covering again just because we're talking about the universe, so why not? So when the universe was much hotter and denser, when the temperature was of the order of MeV over Boltzmann's constant, there were no neutral atoms or even bound nuclei. So this is what I was just now mentioning, which is that when the environment was so hot and dense and excitable, pretty much also known as the photons were disturbing everybody, radiation-dominated universe, you basically could not make neutral atoms and even bound nuclei. So that's what we're going to be talking about now. And I'll give a little bit of an introduction from this chapter, and we will go into a little bit more detail later on, which introduces some of the nuclear physics concepts that we will be needing as well. Hi, Suji Mama. Suji Mama is here. So the vast amounts of radiation in such a hot environment ensured that any atom or nucleus produced would be immediately destroyed by a high energy photon. As the universe cooled well below the binding energies of typical nuclei, light elements began to form. Knowing the conditions of the early universe and the relevant nuclear cross sections, we can calculate the expected primordial abundances of all the elements. So I promised kitty cats in the live, here they are. So, so this is the type of stuff that I was mentioning where if you have light element abundance observations, such as hydrogen, helium, lithium, beryllium, all that stuff, they need to kind of match with what we know happened in the Big Bang nucleosynthesis. Hi, Suji Mama. People are learning physics. Are you gonna... Hi. Oh, hello. Okay. Okay. People are learning physics. So the combined proton plus neutron density is called the baryon density. So this is some verbiage. We will get into more details in just a little bit, but I wanted to tell you about this part goes over the verbiage a little bit. So what we consider this word baryon is protons and neutrons. So the baryon density is basically this, sometimes it's called ordinary matter density, basically as well, because baryons are protons and neutrons, and that's pretty much what makes up ordinary matter. Of course, we also have other things like electrons and neutrinos. We will talk about that as well separately. But the combined proton plus neutron density is called the baryon density, since both protons and neutrons have baryon number 1, and these are the only baryons around at the time. So back in the Big Bang nucleosynthesis era, pretty much you only cared about protons and neutrons as far as the baryons go, and that's what that means, what baryons mean. So thus, Big Bang nucleosynthesis gives us a way of measuring the baryon density in the universe. Since we know how those densities scale as the universe evolves, they fall as a to the minus 3, we can turn the measurements of light element abundances into measurements of the baryon density today. So it's like saying, take the observations of light element abundances and figure out the baryon density today, because we know that those have to match, and we know that nucleus, what the Big Bang gave us in terms of baryons, match what we think of back then. In particular, the measurement of primordial deuterium. So this is an isotope of hydrogen. We will cover it in more detail in a bit. But basically, we can, how cool is this? We can measure this. So measurement of primordial deuterium pins down the baryon density extremely accurately to only a few % of the critical density. Ordinary matter, or baryons, contributes at most 5% of the critical density. So we will talk about this, but this is a huge piece of fact and another way of looking at dark matter, which is that we found that from all this math and observation of baryon density, that baryon density only contributes to about 5% of the critical density, whereas all of the matter, we will see, contributes more than 5%, and the rest is basically dark matter. So we will get into specifics here soon, but that's one thing as well. Big Bang nucleosynthesis gives us something like that as well. Since the total matter density today, so here it is, since the total matter density today is almost certainly larger than this, direct estimates give values of order 20 to 30%. So the total matter density is 20 to 30% of the critical density of the universe, which is, critical density is everything, basically, all the cosmic ingredients. So if the total matter density is contributing to 20 to 30% of the critical density, that means that everything other than the 5%, which is baryon density, is going to be dark matter. And we will get into more details of that, but that's where some of this is coming. That's where we get dark matter. This is an overview level, but that's where we get dark matter. The deuterium measurements are the new measurements in the field. These measurements are so exciting because they explore the deuterium abundance at redshifts of order 3 to 4, well before much processing could have altered the primordial abundances. So these deuterium measurements are going to be very important. By the way, the reference for that is Burles and Tytler, Burles, and Tytler, Tytler, the authors from 1998 who talked about this. So you can look up the paper if you'd like. But basically, these deuterium measurements are very important because we're getting them from very old times, basically, very far away, very old times, well before much processing could have altered the primordial abundances. So this measurement gives us that primordial abundance and also tells us more information about what percentage of the critical density is from this ordinary matter, which was mainly just hydrogen back then. So then another important thing is the basic idea is that light from, so this is the same one, light from distant quasars is absorbed by intervening neutral hydrogen systems. The key absorption feature arises from transition of the n equals 1, that's the ground state of hydrogen, to the first excited state, or the n equals 2 state, requiring a photon with a wavelength of 1215.7 angstroms. Since photons are absorbed when exciting hydrogen in this fashion, there's a trough in the spectrum at this same wavelength, redshifted by a factor of 1 plus z. The corresponding line from deuterium should be shifted over by 0.331 plus z angstroms and much less damped since there is much less deuterium. So we can look at this, but there are now a half a dozen with detections precisely in the neighborhood shown here. Note that the steep decline in deuterium as a function of baryon density helps here. Even relatively large errors in deuterium measurements translate into small errors on the baryon density. So this is about basically what this deuterium measurement tells us about baryon density, and how even if there are errors in that measurement, it leads to very small errors in the baryon density. So it's not like that baryon density of 5% of the critical density comes from some error. And let me give you another definition before I go too far. Basically, I wanted to mention that it's hard to do it without the equations, I will say. I covered it all in the past, but so basically energy density in the universe as a function of time is called rho of t. And basically when you set the time to be now, because rho of course is a function of time, then you get what is called the critical density. So basically, we want to understand what is contributing to the critical density nowadays, and compare it, basically also understand, okay, all of this stuff can only be this much part of the critical density. And so what does that tell us? Basically, that's so I wanted to make sure, and critical density is given by 3 h naught squared over 8 pi g, where g is Newton's constant, the same stuff that appears in all the gravitation type of equations, and h is the Hubble rate, and h naught is the Hubble rate today. And the Hubble rate, by the way, which is a function of time, is given as dA dt over a. So that same a that I talked about, which is the scale factor. So that's it. That's it. Those are all the equations for now, because there's much more detailed coverage of this in a different live. But basically, Hubble rate is h of t. It's a function of time. It goes as dA dt, so a derivative of the scale factor a, dA dt over a. And you can choose to basically say, okay, what is the Hubble rate today? Give it to me. And we call that h naught. Hi, Ben. Checking in. Okay, good job. Hello, Ben. And that is h naught, and the rho critical, this critical density that we've been talking about the universe, is given as 3 h naught squared over 8 pi g, okay? And we know that baryon density, which is neutrons and protons, contribute only to 5%. How we know that, we will talk about it more here soon, but I give you a preview of it, which is that there was a lot of absorption of there was the observation which has to do with basically deuterium absorption that gave us this clue. And also because this deuterium is like a primordial deuterium, it's that old Big Bang nucleosynthesis deuterium. So that is how we know, oh wow, this is how much there was, this is how much there is now, and this matter can only contribute 5% to the total matter density. Because guess what? We have another way which has nothing, because remember I talked about the deuterium absorption, this deuterium measurement, these things. Quasars, the basic idea is that light from distant quasars is absorbed by intervening neutral hydrogen. So this is an interaction of matter with light, right? So the interaction of matter with light might give us something like the baryon density. But guess what? There's other interactions of matter, right, that have nothing to do with light. For example, interaction with gravitation. So by doing different ways of measuring how much matter there is, some measurements have to do with light and some measurements have to do with gravitation, we found that ordinary matter is only 5%, whereas the total matter density is more like 20 to 30%. And the total matter density comes from a different approach, which is a gravitation approach. So dark matter, in other words, you will see how it does interact with gravitation, but it does not interact with electromagnetism, photons, things like that. And of course, if there are ways of measuring the matter that utilizes photons, then of course you're not going to catch it. I am Batman. Hi. Thank you for your knowledge. Thank you. Thank you for coming to the live. Thank you for joining. Thank you everybody for joining. Guillermo, Harper, Ben, I'm Batman, Reese, everybody, thank you so much. So now that I've given you a little bit more overview, I'm going to get into more specifics. I know it's been a lot of material, but I'll say everything in just a second in a little bit more detail and also more organized. Okay, so real quick, where is page 62? You know what? No, first I want to talk about cosmic inventory. There we go. Yes. So I know we are talking a lot about different things. Hi, Stephen. Stephen says, hey, friends. Hello, Stephen. Today we are talking about the universe. So not planets, but the full universe. So I told you very quickly just now about some things. Hi. Yes, I love Jesus, but we're in astronomy right now. Basically, you will see it's kind of funny. Because the Big Bang nucleosynthesis era, that radiation dominated era, was so, photons being so hot, like making everything so hot, dense, energetic, craziness, we actually could not make too many types of elements back then. We didn't have too many types of nuclei to complicate the picture of back then. So it's kind of funny, but the simplicity of the Big Bang nucleosynthesis actually makes our life a little bit easier in that sense, because it's not like we have to look for carbon. There is no carbon back then, right? It's not like we have to understand how much carbon was there in the Big Bang nucleosynthesis, because it was not made. It couldn't be made. And that is consistent with our understanding of the Big Bang nucleosynthesis and how much of stuff you would need to have enough helium nuclei coming together, for example, to make carbon. And also, it is consistent with what we see observationally of what is absorbed by intervening, gas. And that is also consistent with the fact that it was mostly just hydrogen. So it's all this, it's very strange. Cosmology is almost like this very mysterious puzzle, but if you start to put, it's almost like a very big puzzle with a lot of pieces, with a lot of small pieces. But you really can't miss anything. You really can't be like, oh, I can just solve it without this little piece. No, every piece is super important, and you have to understand where it fits. So like those observations of the distant quasar light being absorbed by the deuterium, every little thing is very important, and it informs our understanding and our, equation solving and all of that. Was there a beginning? Yes, there was a beginning. We will talk about it in just a second. First, we will talk about cosmic inventory and what makes up the universe, what are the main cosmic ingredients of the universe. And then in just a few minutes, we will talk about the Big Bang. So yes, there was a beginning. The Big Bang is the beginning. And the Big Bang nucleosynthesis work, which is models for what stuff was there in the Big Bang or what the Big Bang made. Because, the Big Bang is not a useless occurrence. It did make some things. And the universe kind of evolved from there. We will talk about all of this. So the Big Bang, once again, if this is the only thing you take away, the Big Bang's main thing is that it made hydrogen soon after, okay? Aw, well, thank you, I'm Batman. So, I know that these things can be a little bit complicated. So let me say this in a very simple way first. It's not that bad. The universe just has five types of things mainly. The cosmic inventory is pretty much just 5 main ingredients. There are 5 main ingredients of the universe, and you should guess some of them in the chat. But I'll list them now, and we will say a few sentences on each one, and you will see, wow, that's it? Like, the universe is just 5 things. Now, 2 of those things we don't really understand. But we know that the universe is mainly just 5 things. The cosmic ingredients are just a laundry list of 5 items. 5 is not that high of a number. So it's photons, baryonic matter, baryons, what we are made of, you and me, dark matter, neutrinos, and dark energy. That's it. So, so hydrogen is those are examples of the elements. Those all fall under baryonic matter. It's okay. Hydrogen is a good one. Pretty much in any cosmology or astronomy question, if you just say hydrogen, you're probably good. You're probably good. Honestly, hydrogen is a great answer when it comes to the universe. So that's not a bad answer at all. The Big Bang nucleosynthesis includes hydrogen. It's not the main thing in the Big Bang nucleosynthesis because, as I said, radiation-dominated universe, of course, is going to have more photons than anything, right? Photons, electrons, positons, blah, 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 blah. We'll see. We'll get into it. But hydrogen was also part of it. As far as matter goes, hydrogen is the main thing that the Big Bang is responsible for. And from there, we all come, right? From there, we get helium, then we get the first generation of stars, and we start to make other things, including carbon, etc., etc. That's how we're here. We're made from stardust. But of course, for that, we would first need the stars. And for the stars, we would first need the universe to start. And that happened in the Big Bang. So we're talking about the universe now. Literally the entire universe, everything, okay? So don't think just like Earth or this solar system, We were talking about the planets last night, but that's the solar system. The universe is bigger than that. The universe is expanding. So we know that it had to start from the Big Bang. But yeah, let's list the cosmic ingredients again. Photons. We know photons are very important. Look at this light right here. Photons are very important, and photons were very important in the beginning of the universe. So photons, ingredient number 1. Ingredient number 2, baryonic matter. Baryons, which are neutrons and protons. Elements are made of pretty much this. Dark matter. This is something we need. We know there is, but we don't know exactly what it is, dark matter. Neutrinos. This is also another important ingredient of the universe, and it ends up being actually a type of lepton, which is in the same family of particles as the electron. And lastly, important ingredient of the universe is, of course, dark energy, which we also don't fully really understand what it is, but we understand that it is needed for the expansion of the universe. Okay, great. So now we will talk about each one. I was thinking carbon too. Yeah, carbon is more recent. Carbon is made in stars. Stars are more recent. That's a detail. We are a detail. Carbon is a detail. Forget carbon. Right now we're talking universe. Forget carbon. Carbon is just okay. Somebody tell me, what is the atomic number of carbon? How many protons in carbon? How many protons in carbon? Hydrogen, helium, lithium, beryllium, boron, carbon. So carbon is more recent. We are more recent. We're a detail. We're here because Earth is good, life evolved, etc. We had oceans, blah, blah, blah. We're a detail. It's astronomy. Carbon made in stars, whatever. Stars provide the good environment to make carbon. We are now talking about even before then. Even before then. But anyway, because we have this laundry list of 5 items, the 5 ingredients, we will say a few sentences about each one. So the temperature of the CMB photons, the cosmic microwave background photons. So we actually have measurement of photons of this early universe from when the universe was around 300,000 years-ish old, which is pretty young. So because we have this measurement and we have a very precise, extraordinarily precise measurement by the FIRAS instrument aboard the COBE satellite, we have a temperature of this photon, which is around, of these photons, which is around 2.725 plus or minus 0.002 kelvins. And the paper for this is in Mather et al. 1999. The energy density associated with this radiation, we know that, we can write it down. There's an equation for it. The factor of 2, there's a factor of 2 in this equation. It accounts for the 2 spin states of the photon. The energy of a given state is simply equal to P since the photon is massless. So photons are massless, but they are bosons and they behave like bosons, and there's equations we can write down about them. Very nice about photons is that basically the Bose-Einstein function can be written down for photons. We have a way to write down the statistical behavior of photons because photons are basically bosons. Let me say real quick the type of particles as well while we're talking about this. There are 3 types of particles that we know of. Ordinarily, these are bosons, quarks, and leptons, and photons are a type of boson. So all of that is to say we kind of understand how photons work. So if somebody told us, hey, can you do some math with some photons, we can probably do that. And we have. So that's photons. So photons is number one in the cosmic inventory. They were very important, especially in the very, very early universe. They were kind of the main thing. We will talk about it more in just a second when we talk about Big Bang nucleosynthesis, but that's cosmic ingredient number one. Cosmic inventory number one is photons. Yes, 6 protons. Very good. And how many neutrons in a carbon nucleus, if any? If any. So baryons. The next in the list is baryons. Unlike the CMB, so CMB gives us a lot of information, obviously, about the photons. So cosmic microwave background radiation is literally just a bunch of photons hanging out from old times. So making measurements of this tells us so much, so very much. It's been measured to death. I have a picture of it somewhere here. It's been measured to death. It's been studied for decades, like I think at least 3 decades now, or may even be 4 decades. I think it's been known for like 30 to 40 years. So of course, all these people just studied the heck out of it, right? So much has been learned about the photons from that. Baryons is different. Baryons is neutrons and protons. That's what we're made of. We're made of elements. A unique element is given by the number of protons in the nucleus of the element. And neutrons are a thing too in the nucleus sometimes, depends on the element and depends on the isotope of the element. But basically, take all the neutrons and protons of this universe and you will get something called a family of things, and that's called baryons. Yes, 6 neutrons. So 6 protons plus 6 neutrons is 12 things, right? Am I right? If you had to make a nucleus of 12 items, could you do it if I gave you 3 of something that has 4 items in it? If I give you a nucleus with 4 things in it, and I give you 3 of these, 4 times 3 is 12, right? So you will see how this comes up later. So unlike baryons, or unlike the CMB, which is photons, baryons cannot be simply described as a gas with a temperature and 0 chemical potential. Baryons are not like photons. You can't write them down as bosons. Therefore, the baryon density must be measured directly, not via a temperature. So it's to be noted that a baryon density has to be heavily observed. It must be observed by us. We can't just write down equations and be like, oh, this is probably right because it's just a photon or a bunch of photons. No, baryon density, as I was mentioning earlier, by the way, it's given by omega B. This omega number, this omega symbol, big omega, has this symbol like that, omega B. So how do we know about baryons and the baryon density? It's very important. We must not make a mistake with this, because if we screw this up, then we will screw up something else, which is very important that we're going to talk about. Bram Candy, hi. The simplest way is to observe the baryons today in galaxies. The greatest contribution to the density, though, comes not from stars and galaxies, but rather from gas in groups of galaxies. So did you know that there's more baryons? Excuse me. I ate some Indian food earlier today. Can we get 20 likes, Ram Candy and others? Did you know that there are more baryons in gases than in stars? Did you know that, Stephen? So if you look at a certain galaxy or more galaxies even, and you take all the stars, more baryon density contribution is made by the gases, not the stars. Okay, anyway, the greatest contribution to the density, though, comes not from, not from stars in galaxies, but rather from gases in gas or interstellar medium. Interstellar, that movie. Hi. Oh, hi, Sachi. In groups of galaxies. in these galaxies, or sorry, in these groups, omega B, exactly. In these groups, omega B is about 0.02. The second way to count baryons is by looking at the spectra of distant quasars. This is what I was mentioning a little while ago. If you look at the spectrum, as in what light has been absorbed by what, of distant quasars, you can see the amount of light absorbed from these beacons, which is the quasar, is a measure of the intervening hydrogen. How much hydrogen is in between, and hence the baryon density. So from these various ways, we have estimates of baryon density. These estimates suggest that basically this baryon density thingamawitch goes as something like 0.02 with a fairly large uncertainty. A third method is to infer, because we can't be too uncertain here, right? A third method is to infer the baryon density by careful scrutiny of the anisotropies in the universe. Anisotropies. The universe, the smooth universe, the CMB, is pretty smooth. But there is some anisotropies. As we will see later on in another chapter, these depend on the baryon densities. Those perturbations to the smooth universe depend on the baryon density. So preliminary results, there is a paper by Pryke, P-R-Y-K-E et al. From 2001, Netterfield et al. 2001, gives us again another estimate for the baryon density, a little bit more certain now. It's 0.024 plus or minus 0.004 and plus 0.004 and minus 0.003. So there's some errors now on that number, which was 0.02 roughly. The number that was roughly 0.02 is now 0.024 because we're combining multiple ways of measuring the baryon density, okay? So some people getting it from the light absorption from the distant quasars, the spectrum from the distant quasars. Some people getting it from the groups of galaxies and the gases in them. Some people looking at the anisotropies to the smooth universe. Various ways, but you get this number hopefully more and more certainly. Finally, we will see that the light element abundances are sensitive to the baryon density, and that estimates of these abundances pin it down to around 0.0205 plus or minus 0.0018. Cute kitty spotting. Yes, she's here with me learning about baryons. So this number is not obtained with the same certainty by all the different measurements of this number, which is baryon density, but combining. So this is why different people, multiple people should be working on multiple different things, because you could be making a measurement of something that is very important and should be measured in multiple different ways, so that then we combine everything to get the more accurate answer. So right now, the more precise number is 0.0205 plus or minus 0.0018. So the error is plus or minus 0.0018. Pretty small. So remarkably then, these estimates of the baryon density with very different techniques, these all were estimates made for the baryon density, but with very different techniques. They're not the same techniques, okay? But they all kind of agree that 0.02-ish number is pretty much what we're getting, okay? They all place the baryon density at roughly 2 to 5% of the critical density. So like 0.0205 with so much error and certainty measurement done, I mean 0.0205 plus or minus 0.0018, roughly speaking, this is no more than 2 to 5%. Thank you. Good morning. You have some great cat videos. Thank you so much. We're talking about cosmology today, the universe and baryon density at this exact moment. So pretty much when you take 0.02 and you say, okay, that's roughly 2%, Sure, an upper limit E way would be to say that the baryon density is roughly 2 to 5% of the critical density. You know, the total matter density in the universe is higher than this. So there must be matter in the universe that is non-baryonic. So all of the ways in which we have come to this particular estimate of 2 to 5% is the baryon density are all baryon specific. So then if we find a different way to measure the total matter density, because this was the baryon density, and if it is light independent, and we get some other number now for the total matter density, then we have to say that there is matter in this universe that is non-baryonic. And that is the cosmology finding way of saying that. There are other evidences of non-baryonic matter, but we will look at the cosmology way here. So keep in mind, we have now discussed two of the ingredients of the universe. First, we talked about photons a little bit ago. We just talked about baryons now and the baryonic density, which is only contributing 2 to 5% to the critical density, which is the universe's overall energy density of all the stuff that it has. So next, what we will look at is, well, what do we know about matter? Something with mass, something with something, what is matter, right? How much matter there is, how do we know? Well, there is also another way of looking at matter, which is its interaction with gravitation. We didn't really look at that yet so far. So let's figure out what is the total matter density by looking at it from a gravitation point of view. So their food is falling. Baryonic cat food is coming out with the help of gravitation right there. A baryon is basically either a proton or a neutron. Protons and neutrons lumped together are called baryons in cosmology. Matter and energy are equivalent as per relativity, yes. There is a consequence of special theory of relativity which gives us matter and energy equivalence. Indeed. But matter will interact with gravitation. Matter also interacts with electromagnetism. Doro! Hi, James. Hi, Batman. Hi, Stephen. Hi, Doro. So now let us look at, so the critical density of the universe is the energy density of the universe today. We've understood the contribution to it from photons. We've understood baryons. Now let us understand the total matter density. And if the total matter density is only 2 to 5%, then all the matter in the universe would be baryonic, or the ordinary matter that we know and love and are made of. But if we find that the total matter density is something more, then that would give us non-baryonic matter in the universe, okay? You can listen to this live at work too, James. All of the methods of measuring the baryon density mentioned above, that we just mentioned, involve the interaction of matter and radiation. Hydrogen atoms absorbing something, you know, anisotropies in the universe. Remember, anisotropies in the smooth universe is basically staring really hard at the cosmic microwave background radiation and finding perturbations in it and doing some math. So that also comes from a photon kind of way or a radiation kind of way. Looking at gas in groups of galaxies and how much baryon there might be in those gases. Again, those are also pretty much oh, thank you. Please do like the live. Yes, thank you. Those are also, in astronomy, actually, we use the matter and radiation way of measuring things a lot. This type of like looking at spectra, right? You will hear this a lot in astronomy. Looking at the spectra of something, even the sun. Even the sun, you can get the spectra of sun and actually figure out how much stuff is what in the sun. There will be absorption lines by the different elements even in the sun, in our sun. So looking at, what is that? Absorption of light by matter, right? So an interaction of matter with light. That is basically a way of getting something like an estimate for baryonic matter. So it's incredibly common to do that. Now we will look at something else. So simply counting stars works at some level because we roughly know how much mass is required to output the light from a typical star. So even that is the interaction of light and matter. There are, however, methods of measuring the mass of matter that do not rely on the way light and matter interact. These classically have involved measuring the gravitational field in a given system, thereby inferring information about the mass responsible for that field. So we can look at a figure for this, shows the inferred mass to light ratios of many systems ranging from galaxies to superclusters. Historically, this ratio was measured on small scales first. So, nearby our own galaxy maybe, suggesting that the density in the universe was far less than critical as more large-scale data were obtained. So as you do this for larger scales, the steady increase in the mass to light ratio led some cosmologists to speculate that eventually we would find that the density was critical. Bacall and collaborators, we've mentioned Bacall in the past, Bacall, Lubin, and Dorman 1995, Bacall et al. 2000 papers, however, have argued that mass to light ratios do not increase past a distance of around 1 megaparsec. A leveling off occurs consistent with a matter density of around 0.3. So suddenly, now we have a new number. We talked about that baryonic density to be around 0.02. Remember, it was 0.02, quite small. Now we have a total matter density. Hi, Fuji Baba. Yes, baby. A total matter density of 0.3. So 0.02 versus 0.3, very different. 0.02 is much smaller than 0.3. So here, the total matter density is the ratio of the total matter density today to the critical density. Recently, a number of other techniques for inferring the matter density have emerged. So we will see later on that the distribution of galaxies in the universe, I mentioned this briefly, in particular, the power spectrum of this distribution is very sensitive to this matter density. So that distribution of galaxies that I mentioned earlier, which is not random, actually is sensitive to this matter density. Basically saying that maybe dark matter plays a very big role in the distribution of galaxies in the universe, which is incredibly interesting, incredibly. Virtually all galaxy surveys have inferred, so there are some galaxy surveys, let's just see. To mention a few examples of galaxy surveys. So by the way, this is the bread and butter of the cosmology people and all that, and looking at a lot of surveys is very, very common. So to mention three of these examples, the automated plate measuring APM survey to be discussed further in chapter 9 of this book has been analyzed by F. Statio and Moody in 2001, the 2-degree field 2DF by Percival, etc. in 2001, and early data from the Sloan Digital Sky Survey. You might have heard about Sloan Digital Sky Survey, SDSS, very, very common, very, well, not common, very important, well-known survey by Dodilson et al., this book's author. These groups found that the total matter density, this is the total matter density, not just the baryonic matter, total matter density. So measured with means of gravitation, because gravitation is not the same as electromagnetism. Matter can interact with both. In the case of baryonic matter, it interacts with both. In the case of dark matter, it does not interact with electromagnetism. These groups found some numbers as well, 0.14 something something, 0.2 something something, and 0.14 something something. So because we got basically numbers like 0.3, 0.14, another 0.14, a 0.2, we're basically saying that the total matter density is something like, it's okay, let him stay. The total matter density is around 0.2. Okay? Another cosmological probe, and there are some different ways to find there are different papers that found this. Another cosmological probe we will encounter is the cosmic velocity field. The paper for this is Strauss and Willich, 1995, and its relation to the observed galaxy distribution. These are related by continuity equation, a relation sensitive to, again, the total matter density. So even the continuity equation is sensitive. Again, most of the measurements are clustered around 0.3. So another way, so this is many different ways that we're mentioning because that's important. It's important to understand. Another way of measuring the total mass density is to pick out observations sensitive to the baryonic matter density over the total matter density ratio and use the apparent value of baryonic matter density to infer the matter density. For example, most of the baryonic mass in a galaxy cluster is in the form of hot gas. So hot gas must, that's something that has baryons, obviously. The ratio of the mass of gas in clusters of galaxies to the total mass can be measured either by looking for X-ray emission or by looking at the electron-heated CMB in the direction of the cluster. If this ratio is characteristic of the universe as a whole, and it probably is because clusters are so large, then the cosmic baryon to matter ratio is around 20%. Since baryons make up only 5% of the critical density. So this was another way. This is another way of getting this, right? This is basically the universe as a whole. It's a characteristic of the universe as a whole that we're getting. It's a ratio now that we're talking about. And this ratio of the cosmic baryon to matter ratio was found to be around 20%. So now since we know that baryons make up only about 5% of the critical density, the total matter density is now inferred to be around 0.25. So we've got numbers like 0.2, 0.25, 0.3, 0.14. Long story short, it's a lot bigger than 0.02. Right? So another way, yet another way of inferring the baryon matter ratio is by looking for features in the power spectrum of galaxies. If the baryon fraction is truly of order 20%, then there will be wiggles in the spectrum. So this is, oh my God. So 20% is a pretty large number, right? So if baryonic matter was really that big, then you would make wiggles in the spectrum. You would see this as being a bigger feature in the smooth universe, which would be not so smooth, I guess. There are tentative hints of these wiggles in the early data from the 2-degree field survey, and these pin down that ratio to be around 0.15, consistent with the cluster observations. Finally, the anisotropies in the CMB are sensitive to the matter density. So they're sensitive to the matter density, not the baryonic density. That's another thing, right? So recent determinations indicate that the matter density, again, another whole way is 0.16. So we have numbers like 0.2, 0.25, 0.3, 0.14, 0.16. These are the numbers for the total matter density. Given the fact that current best estimates of the Hubble constant give small h to be 0.72, the CMB observations also are consistent with a matter density equal to around 30% of the critical density. So now we're saying that basically taking all of this together, we get 30% contribution of this total matter density to the critical density, where baryonic matter is contributing 2 to 5% of the critical density. The total matter density is contributing 30%. We therefore have an enormous amount of evidence. So we talked about a lot of papers here in short, like quickly. We went over all these different ways of measuring this, all these different papers, all these different surveys and things that they looked at. And basically it is saying that the baryon density is of 5% of the critical density, while the total matter density is some 5 times larger. It's around 30%. Most of the matter in the universe must not be baryons. It must be some new form of matter or dark matter. So all of this tells us that the total matter density is a lot bigger than the baryonic matter density. It's around 30%, whereas baryonic matter is only 2 to 5%. So we are thinking that 25% of the critical density of the universe is dark matter, which we don't know what it is, but here's the cosmological way of putting it. Rotating variables? What do you mean by that, rotating variables? That makes sense. Hard to listen to. Yeah, perhaps. Ooh, can we get 20 likes? Doro, how is Mississippi? So wait, you're vegan and Asian. Okay, welcome to Asia. Oh, yes, I see. I didn't know that that was called rotating variables. Anyway, so now we have talked about the 3 cosmic ingredients in the laundry list of Can vegans study astronomy? Yes, of course, anyone can. Are we not allowed to play in any reindeer games at all? I don't know what that means, but you are most welcome here, Batman, with your vegan stomach, I guess. Welcome to the live. Welcome to Cosmology and the study of the universe. Thank you so much for being here. It's okay, work is going on. Can't gripe. Okay. Yeah, it's only Tuesday. Good luck to you for the rest of the week. And yes, thank you so much for liking the live. Like, share, subscribe. Thank you. Rudolph the red-nosed reindeer had a very shiny nose. And we have just talked about the photons. And baryonic matter is very low. It is only 5%, roughly max, of the critical density. And the total matter density is around 30%. So we've talked about photons, baryons, and dark matter now, okay? Total matter density is much, much bigger than the baryonic density, which has given us yet another conclusion, yet another evidence of dark matter in this universe. And we also see that that dark matter is, or the total matter density is what the certain things in the universe are sensitive to. They're not sensitive to, that was good, thank you. Oh, good. They're not sensitive, like galaxy distribution in the universe is not sensitive to baryonic matter density, omega B. The galaxy distribution not being random is sensitive to total matter density, which is, of course, as we saw, dominated by dark matter, not baryonic matter. Whatever dark matter is, we don't know what dark matter is, but that's what makes up total matter density. And that's what makes up total matter density. And certain important and interesting things are sensitive to this total matter density, which is, of course, dominated by non-baryonic matter. So interesting indeed. It's like a puzzle, and dark matter is a piece of it. It's a big, important piece of it. We, of course, don't understand it really well, but it's undeniable. Basically, not nervous, self-conscious. Now she's going to be all nervous. Dark matter is so very important. We still don't know what it is, but it's undeniable. That's the word. It's an undeniable cosmic ingredient. I came into singing hour. Rudolph the red-nosed reindeer had a very shiny nose, luminosity, not dark, made of baryonic matter. Indeed, Rudolph's nose, interacting with photons. Total matter density of the universe is a lot more than 5%, which is the max baryonic matter can be. Grimmy, you should like the life. Okay, we've talked about the 3 ingredients. Now, 4th ingredient is neutrinos. So the 5 ingredients I mentioned were, again, photons, baryonic matter, dark matter, because total matter density is bigger than baryonic matter. Neutrinos, I can't hold these fingers up by myself apparently. Neutrinos, and then dark energy. So we will read a few sentences about neutrinos. Thank goodness they're fermions, so there will be a way to write down equations for them as well. And remember, neutrinos are also highly elusive kind of particles that were actually a candidate for dark matter. Remember, we talked about that in an astronomy type of topic. We talked about dark matter candidates from an astronomical, from an astrophysical or astronomy point of view. And we saw that neutrinos were in fact quite a celebrated, decorated dark matter candidate. We discarded them as being really what dark matter is made of because they're too low mass. But we will consider them as an important, undeniable ingredient of the universe. Nonetheless, of course, because neutrinos, as you've seen already, when we talked about stars too, remember how stars, when they're dying, will often release and lose a lot of energy in the form of neutrinos, because neutrinos will escape very easily. Neutrinos are very elusive; they escape easily. So sometimes, because they can go through things easily, they don't interact with much on their way to things, right? So, or on their way out of things. So it's kind of like neutrinos will easily break up with you. Thank you. Yay. Neutrinos will easily break up with you and they're gone before you know it, is one way of thinking about them. So they're not dark matter, probably. Dark matter is probably not neutrinos, but they're an important ingredient of this universe. So the next component we will need to consider is the neutrino. Unlike photons and baryons, cosmic neutrinos have not been observed. This is old. Neutrinos have been observed now. That's true. When I take my water break, that's when you guys really break out into song and dance. So I think it is a celebratory moment. It's a momentous moment. So neutrinos, astrophysical neutrinos, by the way, have been observed at this time. This book is a little older, but basically the long and short here is that neutrinos are, of course, fermions. They can be described by momentous moment. They can be described by the Fermi-Dirac distribution system of describing things. And basically, I'll summarize it before my bathroom break. As you guys know, it's time. Sneaks out for a bathroom break and drink break too. 7-hour break. Yes. I drink a lot of water and I have to go to the bathroom. Not right now, but I will in a bit. And actually, I'm not good with time. Once I get distracted. I have a creative mind. So when I do something, I get distracted and I don't know exactly how long it's been. Sometimes I'm on my tablet in the bathroom. And I'll even read your comments and then I'll get distracted. And it's been an hour. So we can now evaluate the energy density of neutrinos in the universe. Let's sum up what we know about the cosmic abundance of neutrinos. 1 spin degree of freedom for neutrinos. Neutrino has an antiparticle. Of course, there are anti-neutrinos. Oh my gosh. 3 generations of neutrinos. We know that there are electron, muon, and tau neutrinos. Neutrinos are fermions. Don't ban him. I need the watch hours. Neutrinos are fermions described by the Fermi-Dirac distribution function. I'm scared of someone saying something now because Doro will ban you, man. He will. Neutrino temperature is lower by a factor of 4/11 to the 1/3 since photons are heated by the positron electron annihilation. So we will soon talk about Big Bang nucleosynthesis, and you will see how there was a cosmic breakup between the hot soup of photons, electrons, positrons. Hi, Fuji! Come, Fuji! Oh, Fuji's playing. Oh, Fuji Baba. Hello, Fuji. Fuji has brought me a gift. But sometimes gooners need to go. That's very true. I think we struggled without you last night, Doro. It was quite a scene here. But anyway, basically, those are certain certain sort of, I guess, fun facts about neutrinos and things about them. We will come back to it in a little bit more detail in the section when we talk about Big Bang nucleosynthesis, and we talk about at one point there was a cosmic level breakup between neutrinos and photons, electrons, positrons. So neutrinos is also an important ingredient of this universe. In fact, they have been around for a very long time. Their journey is slightly different. We will get into it in more detail, but they're also an ingredient. So that was the 4th ingredient of this universe, okay? I take 17-hour water breaks just because I like to get people mad at me. I suck with time too, Grimmy can tell. Grimmy reminds me often. Are you the type of person who be in the hotel with all your colleagues and everybody's ready and you're not? Because that's how I am. I divorced my wife for you. Oh my gosh! This is what scared me. I thought after this comment, you're gone for good, Batman. But thankfully, the moderators are being very moderate today. You said something funny finally. I'm not Asian. My little Osha. Oh! Aww! Yes, the universe is a cake, and we are currently talking about the ingredients of it. I dropped my phone in the litter box. So that's a great point that you bring up, Doro. I have wild hair. So, yes. I don't know what that means, but okay. Wild hair. Wilderness in your hair? So you just mentioned that the universe, it's like food, ingredients, right? Oh, I can't even read your comments anymore. Doro is deleting them. 30% total matter density. So, it's almost like these 5 ingredients that we're talking about: photons, baryons, dark matter, neutrinos, and dark energy. We will talk about dark energy in the last bit here. These are like ingredients of a cake, but we haven't fully understood how it's all baked. We get it. It's almost like we get it. It's almost like somebody gave us all the ingredients of a cake. They didn't quite give us all the recipes and everything, but we know the quantities and things in terms of the ingredients pretty well. We're given it, but we still somehow don't have a cake. We still have to figure out exactly how everything is baked together to make the cake. And so it is true that we are talking about the ingredients of this universe, but we may not know exactly how everything works. For example, we don't know what dark matter is. And the last ingredient we'll talk about today, dark energy, we don't know what dark energy is either, but we will talk about it right now. Okay, Batman, everybody, thank you so much for being here. Calm down and listen to this last part of this cosmic ingredient chapter. So cosmic ingredients: photons, baryons, dark matter, neutrinos, lastly will be dark energy. We will talk about that right now. So there are 2 sets of evidence pointing toward the existence of something else. Something else. Something beyond the radiation and matter. Something beyond photons, radiation, baryons, ordinary matter, that is, dark matter. Even dark matter is matter, right? Because dark matter, the way they knew that there is dark matter, the topic of total matter density, it comes from interaction with gravitation. So that's dark matter. It's still matter. But there is something beyond all of this. So dark matter, they call it dark matter because it does not interact with light. Dark energy is a name given to this phenomena of the expansion of the universe, this negative energy of vacuum, etc. So that is more. Oh, actually, we will talk about this, the naming of it. So hold tight, hang tight. So The first comes from a simple budgetary shortfall. So the evidence of dark matter comes from a simple budgetary shortfall. The total energy density of the universe is very close to critical. We expect this theoretically, and we observe it in the anisotropy pattern of the CMB. Yet, the total matter density inferred from observations is only a third critical, right? Because it's 30%. 30% of the critical density. The remaining two-thirds of the density in the universe must be in some smooth, unclustered form, dubbed dark energy. So we know that 30% of the critical density is, the matter density, 25% of that is dark matter. But then what is the remaining two-thirds? Role model. I like that. So this remaining two-thirds is dubbed dark energy. We will read a note about this actually. So by the way, remember how it came from Einstein having to face the fact that general relativity equations were written down to describe gravitation, and this universe under gravitation should be collapsing. So why doesn't it? So in order to balance things out, he had introduced something called a cosmological constant. Remember from our discussions from a while ago when we were covering Einstein's work from this book called Einstein's Cosmos by Michio Kaku. So the cosmological constant was simply to balance out the gravitational force in the universe, which should make it collapse, but instead it was balanced. But actually, things were taken further when we realized that not only is gravitation balanced in the universe, but actually the universe is expanding. And then we realized that not only is it expanding, actually the expansion is accelerating. So it has become incredibly important, even more important than 100 years ago to understand what this is. But that's how it got started. The cosmological constant is not a new concept. It is approximately 100 years old at this point. For 100 years, we have known that there is something called the cosmological constant, which you need as an anti-gravity in this universe. Even before, we had somebody, good person like Hubble, giving us a picture of the universe and telling us that there are actually other galaxies, and this universe that we live in is actually expanding. So even before then, in the 20s, if not a little bit earlier even, we had to basically write down this thing called lambda, or cosmological constant. After the discovery, quite a bit of attention was focused on choosing an appropriate name. So like that whole cosmological constant context. Cosmological constant, everybody's initial moniker, is too restrictive in that the energy density is constant at all times, and we do not yet know that this is true of the dark energy. Variable cosmological constant fixes that problem, but introduces an inherent contradiction, variable and constant. Variable lambda, using the Greek letter reserved for the cosmological constant, is too obscure. Quintessence is a good choice. It expresses the fact that after cosmological photons, baryons, neutrinos, and dark matter, there is a fifth essence in the universe. So dark energy really is the fifth essence of the universe, the fifth essential ingredient of the universe that we need to explain everything. So without this fifth essence or fifth ingredient, we would not be able to explain what all is going on in this universe, including its expansion. So it's all very well to talk about, everything else, gravitation, all the consequences of having matter, etc., etc. But that still does not explain the expansion. So for that we need dark energy, the fifth essence. Okay? It seems to me that dark energy has become a bit more popular, with quintessence referring to the subset of models in which the energy density can be associated with a time-dependent scalar field. So they have a few different models, of course, of okay. Ooh, can we get 30 likes in this live? We have 20 likes, but could we get 30? Is that possible? So, the second set of evidence for dark energy is more direct. Given the energy composition of the universe, one can compute a theoretical distance versus redshift diagram. And then this relation can then be observed or tested observationally. 30? Yes. So here's what that is. In 1998, two groups, Rice et al., Rees, maybe R-I-E-S-S et al., 1998, Perlmutter et al., 1999, observing supernovae, reported direct evidence for dark energy. So this will be very important. The evidence is based on the difference between the luminosity distance in a universe dominated by dark matter and one dominated by dark energy. So basically, if you did not have dark energy in the universe, then pretty much you might be saying that at this time, the universe is dark matter dominated, right? So it's almost like, and because in cosmology, you can develop different models for the universe. You could write down a model which is more matter dominated, or you could write down a model which is more dark energy dominated. So you could see, and then you could compare, and you can say, well, when I do the math with mostly dark matter, does that match my observations for these supernovae data? Or when I, don't distract me, when I make the model have dark energy, does that more closely match the supernovae data, which tells us the evidence of dark energy? So again, it's about comparing your model answers with your observation, which should tell you something, right? So what is the density? I think we talked about that yesterday. So, actually, no. We mainly covered Jupiter and Saturn yesterday. We will talk about the last two planets next time. I am Batman. So, we will keep going for now with dark energy. More concretely, the luminosity distance. Phone is already dying, guys. The luminosity distance can be used to find the apparent magnitude small m of a source with absolute magnitude big M. Magnitudes are related to fluxes. Since the flux scales as dl to the minus 2, the apparent magnitude the apparent magnitude small m is given by big M plus 5 log of dl plus a constant. So there's some math. Now, there's more people. Can we do 30 likes? Can we get 30 likes? So I will summarize for you what actually happened. It's very interesting. Basically, these two groups that we mentioned for the dark energy evidence, Rice et al., R-I-E-S-S, and Perlmutter et al. In 98 and 99, they're talking about measuring the apparent magnitudes of dozens of type 1a supernovae, which are known to be standard candles. That is, they have nearly identical absolute magnitudes. So in astronomy, we have this concept. So this is cosmology, but you will see now the overlap of cosmology with astronomy, which is that let's say that we have a bunch of candles. In astronomy, candles are basically where you have events, objects, whatever you want to say, with a standard absolute magnitude of luminosity. So it's well understood, and you're going to use this as as basically almost like a tool. So although they were able to place tight constraints on dark energy using the many supernovae that they detected, we can get a feel for the measurement by simply considering two of these. So we will walk through it with two of these supernovae. Consider then supernova 1997 AP, found at redshift of z equal to 0.83. So we're just giving you an example supernova now, a couple of them to understand this process, okay? So supernova 1997 AP was found at a redshift of z equals 0.83 with apparent magnitude small m of 24.32. And supernova 1992P, another one, was found at a lower redshift of 0.026. So the two redshifts are 0.83 and 0.026. One is much closer than the other, okay? And this lower redshift one has an apparent magnitude of 16.08. So the two apparent magnitudes are 24.32 and 16.08. Again, different, right? Since the absolute magnitudes of these are the same, so why is this? Why are we choosing these two supernovae? Because they are at two different redshifts with two different apparent magnitudes, but actually they are standard candles because their absolute magnitudes are actually the same. So the difference in apparent magnitude is due solely to the difference in luminosity distance. So what is that? This is going to be 24.32 minus 16.08. Those are the difference. That's the difference between the apparent magnitudes. That's going to be connected to the redshift z. The nearby luminosity distance is independent of cosmology. So the other thing now is not only do these things, they're standard candles, they have the same absolute magnitudes, but they have different apparent magnitudes. But one of them, thankfully, is closer. So the one that's closer is not going to be affected by expansion or cosmology. So that one, we can say, is simply equal to z over h naught, so the redshift over the Hubble naught. Therefore, the only unknown remaining is fixed by the observations to be h naught dl at a z of 0.83 to be 1.16. So now we have a new number. So basically this h naught dl for the 0.83 redshift one is 1.16. In a flat matter-dominated universe, so you can put matter-dominated or the omega m to be 1, the luminosity distance out to z equal to 0.83 is equal to 0.95 h naught, actually to the minus 1, but we will forget about that. So the number that is 1.16, when you make the universe matter dominated, is 0.95. Whereas a universe with matter density of 0.3, you get the other number to be 0.7. So this basically gives you a luminosity distance of 1.23. So your options are 1.16, 0.95, and 1.23. It's almost like you're putting in the different number for the total matter density, which will of course give you a different number for dark energy's density. And then you're saying, okay, if the total matter density is 1, then you get 0.95. If the total matter density is 0.3, which is 30%, then you get 1.23. The measured number is 1.16. So there's three numbers, 0.95, 1.16, and 1.23. 1.23 is a little bit closer to 1.16, or it seems a little closer. We will keep going though. The apparent magnitude of this single distant supernova then suggests that dark energy pervades the universe. So basically, we didn't know, let's just pretend that we didn't know that dark energy was there, and we can just vary the total matter densities number as much as we want, it's basically the other direction when we get a number out for the distant supernovas H0 DL, we get from there that, oh my God, actually the dark energy dominated universe is the one that explains that number. So that's how they used the supernova data. They basically used a bunch of standard candles, so events or objects, if you will, of absolute magnitude being the same, but at different redshifts. So the really, far away ones, the high redshift ones, if they ended up having a different apparent magnitude, and that gave us a number for this H0 DL, plugging everything into the models, it gives us that actually the universe that supports this type of thing happening is the dark energy dominated one. Okay? Yes, we will talk about the flat universe. So the universe being flat is a model, and you can actually question the flatness of the universe. The Earth is round, we know that, but actually whether the universe is flat or not, what curvature the universe has is also is dependent on the model that you use. But yeah, we think that it's flat. But we will talk about that as well. Good question, good comment. Good comment. So all of this type of thing, basically there are two free cosmological parameters, matter density and the cosmological constant, something we now recognize as one possible form of dark energy, one in which the energy density is constant. Note that theorists' dream universe, flat and matter dominated, is excluded with high confidence. So this dream where the universe is flat and matter dominated is actually excluded with a high confidence at this point due to doing stuff like this. Like you can, in the cosmological models, you can give these matter densities, total matter densities, the dark energy density, anything you want, right? In the models, you can make them 1, 0.3, 0.7, whatever, but it's really the one that then gives you the best match with observation, which will tell you sort of the more accurate model or the theory for dark energy or the number for the density of dark energy. Okay, so I have there is a little bit more detail here. We will skip it and we will try to finish this out with this particular discussion here. Let's see. Good night, Stephen. 14%. Okay, we will keep going for a little bit longer here about this dark energy stuff, okay? So, turns out that there is another thing that they were able to vary. So, within this work of figuring out what the dark energy density number should be, there's actually another little variable that they figured out that they should vary. It's called the small omega thing. So let me talk about that. So they realized that they should be plotting this another thing called equation of state versus the total matter density and see which one fits best with explaining how the universe is the way it is, okay? So basically, let me introduce that here. To open up possibilities, basically this equation, let me go back a bit here and tell you about this particular equation. Thank you for being here. Thank you for coming to the live. So there's a conservation law in an expanding universe. From there, we're gonna get more information. The only way for this equation to be satisfied with constant energy density is if the pressure is equal to minus rho. One might imagine energy with a slightly different pressure and therefore energy evolution. So what we're saying is this: there's a new variable being introduced here, small w, or just small omega, which is the big P over rho, where big P is pressure. A cosmological constant corresponds to omega equal to -1. So if you're saying that the dark energy density is given by a cosmological constant, then your omega will be just purely -1. Matter dominated would make omega to 0 and radiation to omega equal to 1/3. With this new freedom, let's see what the supernova data imply for the equation of state of the dark energy if we fix the universe to be flat. So fixing it to be flat, we actually see that values of omega greater than -0.5-ish are disfavored. A cosmological constant is consistent with the data, but it is by no means the only possibility. So even the cosmological constant is a possible way of saying, of providing energy density number for dark energy. There's more possibilities. And then we can integrate and all that. But let me show you what I mean here. Equation of state is in the y-axis, and total matter density is in the x-axis. And there's lots of different possibilities here. But if you're greater than 0.5, then that's disfavored. And by that, I mean greater than 0.5 for the, or sorry, greater than -0.5 for that equation of state. Okay, so we'll keep going. So if omega is constant, this expression, which we now have for the rho density of dark energy, agrees with our knowledge of the cases explicated above for omega equals 1/3, 0, and -1. So now that we have more tools at hand, basically to describe dark energy as well at this time, as far as a density goes, or a number of possibilities of density goes, well, we can actually now think about a matter radiation equality epoch of the universe. There might have been a time in the universe where pretty much things were equal between matter and radiation. So let's talk about that. So the epoch at which the energy density in matter equals that in radiation is called matter radiation equality. It has a special significance for the generation of large-scale structure and for the development of CMB anisotropies. So we keep mentioning about the CMB anisotropies, even though the CMB is considered to be largely smooth, but there are at higher orders considered to be or found to be some perturbations or anisotropies that are actually kind of important. So because perturbations grow at different rates in the two different eras, so matter dominated era versus radiation dominated era actually have different implications in terms of these perturbations. It is therefore a useful exercise to calculate the epoch of matter radiation equality. To do this, we need to compute the energy density of both matter and radiation and then find the value of the scale factor at which they were equal. So remember that scale factor A comes back here. So we basically are going to set this rho, or the total energy density in radiation, over the energy density or the critical energy density to be equal to omega r over a to the 4. And to calculate the epoch of matter radiation equality, we will take these, equal them, and you get a certain redshift or a certain expression at which this happens. So as the amount of matter in the universe today goes up, the redshift of equality also goes up, right? For our purposes, it will be very important that the redshift of equality is at least several times larger than the redshift when photons decouple from matter. Thus, we expect photons to decouple when the universe is already well into the matter-dominated era. Okay, so we will summarize all of this in just a second here. Let me... Well, there are different evidences of dark matter. I would want to ask which one are you talking about. Then we would get some more context of what question you're asking about dark matter. Ajay. But yeah, dark matter is indeed something that we don't understand. So, Americans valued women. Oh, okay. So let us summarize